Alright, so this video is about solving rational equations. And to start, we need to talk about what it actually means to solve. So to solve means to find the value of the variables or variable that make the equation true. Okay, so you're looking for the value of the variable that makes the equation true. So in this course, we're going to be looking at equations that have just one variable that we're solving for with rational equations. So to start talking about this, I'm just going to look at a really simple example. Something like 1 over 3 equals 5 over x. This is a rational equation because I have two expressions that are equal to each other, and those two expressions are rational. So we all know how to solve this. We've been looking at problems like this for years and years. But I want to address the question about what this kind of question is asking in a grade 12 context. So, algebraically, we can consider like 1/3, that's equivalent to 5 out of what quantity, like just proportional reasoning wise. But if we're talking about a function, then this is really asking us about this function 5 over x as a graph. And then we're asking, where is that graph at the value of 1/3? So if I were just to sketch this out, we know that 5 over x has a horizontal asymptote at 0 because the numerator is degree 0 and the denominator is degree 1. So the denominator has a higher degree than the numerator. So we know it has a horizontal asymptote at y equals 0. And we also know it has a vertical asymptote wherever the denominator is 0. And so that happens when x is 0. So we have a vertical asymptote here. And so it's basically just the graph of 1 over x, but because the numerator is a 5, we have a vertical stretch. So it looks something like this, where we have, it's kind of a little bit more stretched out than the regular 1 over x. So this is the graph of 5 over x. And this question, when is 5 over x equal to 1/3, is asking us, well, where is this graph at a value of y of 1/3? So solving this question means finding the place where that occurs, which means finding the x value where that happens. Okay, so just so we have some like graphical context for what this question is asking us for, now we can talk about algebraic ways to solve it. So lots of different algebraic ways to do this, of course. You can use a scale factor, you can cross multiply, you can do all kinds of things. But what I want to do is I want to talk about some strategies that are going to be relevant for us as we continue to work with more complex functions. So one thing I could do is I could, right from the start, I could establish a common denominator. Because I know that if, for example, I had like 5, or say, I don't know, 150 over x is equal to, oh sorry, that's not what I want to say. If I have like 150 over 2 equals x over 2, then I know that x has to be 150 because we can see that the denominators are the same and these two expressions are equal to each other, so we can conclude, okay, well, the numerators have to be the same. So that's one way that we can approach this, is by establishing a common denominator. So that's what we're going to do. So in order to establish a common denominator, I have to identify what that lowest common denominator is. So in this case, that's going to be 3x. So that means I need both of those rational expressions to have 3x as a denominator, which means I have to multiply this expression by x on the top and the bottom, and I need to multiply this expression by 3 on the top and the bottom. That allows me to get a common denominator on both sides. So we have x times 1, which is x, over 3x, and then we have 15 over 3x on the other side. So now that we have this common denominator, we can see, okay, well, something over 3x equals 15 over 3x. So since the denominators are equal, that means the numerators have to be equal because the two statements are equal to each other. So therefore, I can conclude from here that x is 15. So this is one way to approach a problem like this, is you can establish a common denominator. That's what we just did. Okay, then once you have the common denominator, you're able to make a conclusion about the numerators. Another way to kind of approach this problem is to do something that I do actually want you to get in the habit of doing, which is starting by changing the question a little bit to be equal to 0. So that means in this scenario, I'm going to subtract 5x from both sides. So I'm going to get 0 on one side of my equation. Now when I do this and I establish a common denominator, I'm going to do the exact same thing as before, multiply this fraction by x over x, and multiply this fraction by 3 over 3. And I get x over 3x, and I get negative 15 over 3x, and this equals 0. So really, like, we're looking at the same kind of thing that we're looking at over here. It's just that this equation now, I'm able to conclude in a kind of a different way that when this expression on the left is equal to 0, that's just all the places where the numerator is equal to 0, okay? Because we know that if the numerator was a 0, then that would mean that the value of the left side would be 0. Whereas where the denominator is 0, that would mean that that function's undefined. That's not the same thing as 0. So this is true when, like this earlier statement is true, when x minus 15 is equal to 0, okay? So we can really kind of only look at the numerator, then we're able to say that x is 15, okay? Of course, you could make that conclusion just from this step right here, and to say that x is 15. Okay, so just to provide some context, like a really simple example of the graphical interpretation of what it means to solve a rational equation, and a couple of different strategies that we can employ. The idea being that you're establishing a common denominator so that you can make some kind of conclusion. Of course, we have all kinds of other strategies that we could use that we've learned in grade 9, like we can cross multiply. So doing that, then we're left with 1 times x equals 3 times 5, which is 15. You get to that answer right away. Totally. The problem with cross multiplying as a strategy with advanced functions that we're in right now is that it only works with equations. It doesn't work with inequalities, which is where we're going next, okay? So cross multiplying only works for equations, and we'll go into why that is later. Whereas these strategies of establishing a common denominator, those strategies are going to stick around. We can use those with polynomial inequalities, rational inequalities as well. We won't have to like have different strategies for different types of problems. Okay, so let's move on. Let's look at another example that looks a little bit more like what we're used to in grade 12. So here again it says solve 4x minus 1 over x minus 5 is equal to 0. What is this asking? Let's start here with this question. What is this question actually asking us to do? Well, if we consider that this left side of our equation is a function, then we're asking where does the graph of that left-sided function cross the x-axis? Okay, that's what that question is asking us. So again, we could draw a graph of that function. We know that it has a horizontal asymptote at 4, is linear on the top and the bottom, and we can find all kinds of other information about it. But basically, we're asking when does it cross that x-axis? When does that occur? Okay, so let's tackle it. So one way, of course, that we could do this is we could use all of the skills that we have to graph this function, right? We can spend the time and make a really great graph and then observe where it's equal to 0. That would totally work. It's just the disadvantage of doing that, of course, is that it's long. We know that it's a long process to graph a rational function. So what we can do instead is we can see if there's an algebraic strategy that we can employ, similar to the ones that we've kind of looked at before. So one thing that we could do is we can observe that this equation could only be true. This equation could only be true if the numerator is 0, okay? Because when you're dividing, there's no way to get 0 as an answer unless 0 is the thing that you're dividing. I like to use the example of like a cookie. If you take a cookie and you cut it into a bunch of pieces, that's really what division is, right? You're like cutting up something and dividing it amongst people evenly. So imagine it's a cookie that you're dividing amongst people evenly. You can cut that cookie in so many different ways and however many different times, and never, ever, ever will the cookie disappear by your cutting it, okay? Even if you're, cutting it to, infinitesimally small pieces, the idea is the cookie never goes away. So you can never get 0 as an answer when you're dividing unless the thing you're dividing by, or dividing itself, is 0. So from here we can conclude that this is true, this statement is true, when the numerator is 0. Okay, we really only have to kind of consider the numerator, because that's the only way that we could get 0 as an answer here. So the denominator's there. It's an important part of this problem, but it's not relevant just for this algebraic question of when is that equal to 0. So of course we can rearrange this equation, add 1 to both sides, divide by 4 on both sides, and we get x is 1 over 4. So looking on our graph, we know that we would have an x-intercept here at 1 over 4. So our graph probably looks something like this. And then the horizontal asymptote would be at 5. Oh, I'm totally lying to you. Our graph might not look like that because we have an asymptote vertically at 5 as well. So our graph probably looks more like this. Okay, so anyway, so there's one algebraic way to get to that answer, is just observing where the numerator is 0. Okay, another way that we could tackle this is we could look at taking 4x minus 1 over x minus 5. And we could multiply both sides by x minus 5. And we can see that when we do this, we're left with just the numerator, because the x minus 5 on the top and the bottom, they divide out. And then 0 times x minus 5 is 0. So we're left with that expression anyway. Okay, that same expression of 4x minus 1. And then we're just setting that's now equal to 0. So yeah, we can do that. Again, the danger of doing this is that what we just did, multiplying by a value that contains x on both sides of the equation, is not allowed with inequalities. So we'll talk more about that later. So right now, the safe thing that you can always do is when you have an equation equal to 0 and that equation has a fraction on the one side, then you just need to observe where the numerator is equal to 0. Okay, so you can take that numerator kind of away on its own and solve that equation to find where it's equal to 0. That's one way to kind of tackle this. And then we'll add more to that when we talk about inequalities. Okay, another example. So here it says x plus 2 over x minus 1 equals 2x minus 3 equals x plus 4. So what is this asking? Again, let's talk about what that means graphically. So one way to interpret this is to see that this side is one function and this side is another function. So that when we ask ourselves, when are they equal, we're really talking about the point of intersection. Okay, so this is like interpretation 1. Okay, the left side function and the right side function. Okay, so that's one way that we can look at this. So a really long way to solve this problem is to graph both. Graph both functions and then find their point of intersection. But of course we know that that strategy of graphing to solve is a really long strategy. So we do want some algebraic strategies to back that up, and that's fine. I want to talk about another way to interpret this problem. And that's to kind of change the question a little bit. So I could take this, this given equation, x plus 2 over x minus 1 equals 2x minus 3 over x plus 4, and I can subtract the 2x minus 3 over x plus 4 from both sides. In doing that, what I do is I've effectively gotten rid of that term on the right-hand side, and I've moved it over to that left-hand side. So now I have an expression that's equal to 0. And 0 is a really nice value to have on one side of your equation, because we have all kinds of rules about when things can be equal to 0, and we have lots of strategies to deal with that. So this is a really cool way to do this. And the reason that I emphasize this is that this is what we have to do when we're talking about inequalities, really. Unless we want to do like just always graphing the two functions, which would be strenuous. So let's talk about what this means. When I do this, I basically change the question, so I'm creating a new function. So this is not f of x, the left-sided function. It's not g of x, the right-sided function. It's like a totally new function, so I'm going to call it h of x. And so this is asking me, where is this new function crossing the x-axis? So when we talk about inequalities, it will be easy for us to say, where is this new function above the x-axis? Or when is it below the x-axis? Those are easier questions to answer if we've already talked about where the function is equal, like equal to 0 or at the x-axis. Okay, so we're going to get to that idea of where the function is above or below when we start talking about equalities, which is next. Okay, so now we have this new equation that we're going to use. So this is what I'm actually going to use to solve over here. Okay, so again, like last time, there are lots of different ways that I could solve this problem. One thing I could do is I could multiply by the lowest common denominator, which is what the textbook does. However, I want to give you a strategy that will continue to work as we move into talking about inequalities as well. So that strategy that I'm going to emphasize is going to be to establish a common denominator. Okay. And that makes sense to do because anytime you have an expression that has multiple fractions in it, it should be our inclination to try to put those two fractions together. So I need to consider what is the common denominator that I should use. So I'm aiming for the lowest common denominator. That lowest common denominator is always going to be the combination of those two or three or however many fractions you have denominators together. Okay, so this is the denominator I'm going to try to obtain. So I have x minus 1 and x plus 4 on the bottom of my equation. And now I need to have multiplied both fractions by something. So I know in this one, the first expression, in order to get x minus 1, x plus 4 in the bottom, I have to multiply the top and bottom by x plus 4. Okay, so that I'm still obtaining an equivalent fraction by multiplying the top and bottom by the same quantity. So now I'm going to do that here as well. Whereas in my second term here, I already have the x plus 4. I need the x minus 1. So I'm going to multiply the top and the bottom by that x minus 1. Okay, so now we have this new equation that has one denominator, and that denominator is x minus 1 times x plus 4. Now from here, what I'm going to do is I'm just going to expand and simplify. So here we have x squared, and then 6x, and then 8. And then we have, I'll do this in multiple steps so I don't lose you guys. So 2x squared, and then we have negative 2, and negative 3 makes negative 5x, and then negative 3 times negative 3 is positive 3, or negative 3 times 1, sorry, over that same denominator. And now I'm going to continue to collect like terms. So I have x squared minus 2x squared, so we have negative x squared. And then I have 6x minus negative 5x, which makes 6x plus 5x, which is 11x. Then I have 8 minus 3, which is 5. Okay, so this is beautiful because now we have this equation, and one side of our equation is 0, and we know that being a fraction, the only way that this fraction can be equal to 0 is if the numerator is 0. So only because we're looking for it equal to 0, okay, this idea of equality, because it's equal to 0, that's only possible where the numerator is 0. Later, when I'm solving questions like where this is greater than or less than or equal to or greater than or equal to, then I need to look at more than just the numerator, okay? But for now, algebraically, we know this can only be equal to 0. When the numerator is. Okay, so because of that, I can use that here. So this expression, or this equation rather, is true when the numerator is equal to 0. Okay, so I can kind of take that apart. I just want to put this in a cloud because this is really important for when we get to inequalities. So now I just have a quadratic equation that I can solve. And strategies that I have to solve a quadratic equation are I could factor, I could use polynomial division if it was a higher degree, or I could just use quadratic formula. So here it doesn't look like it's factorable, so I'm going to use quadratic formula. Okay, so I'm going to sub in all my values. And these will be my solutions for x. Okay, these are going to be the possible values where my function could be equal to 0. Okay, so now I'm going to pull up my calculator. So the square root of 141 is approximately 11.87. So my two answers are going to be negative 11 plus that value. So about negative 0.44. And my other possible value will be negative 11 minus that value. Now, normally what I would do is I wouldn't be using this rounded value to do this calculation here. I would use the exact value. I'd keep it in my calculator. However, the calculator that I'm using is just a little bit too simple, so it doesn't let me do that. So just a heads up. When you can, always, don't round until the very, very last step. Okay, so we have these two answers. Once we have these answers, it's really important to go back and consider if these answers are valid. So from now on, that's actually where we should start. Okay, so when we look at that original question, we should ask ourselves, where is this function even valid? Where is this equation, where does it not exist? Okay, so right away, the first thing I want to think about is if it's not already factored, I want to factor it. And then if it is already factored, now I can say, okay, I know that I have restrictions at positive 1 and negative 4. So I kind of have this in the back of my mind. Now that I have some answers for x, I want to make sure that none of my answers are in those restrictions. So I go down and I think, okay, these ones are both okay. They were not in my restrictions, so they must be valid solutions. Okay, so these are my answers. Now again, let's just go back to after we've done all that algebraic work. What does this mean? Like, what did we just find? Like, what is all that work that we just did? What was that for? So just want to remind you that this question is all about these graphs, right? Like we have this graph equals this graph. And what we just found is that those two graphs would be equal to each other in two places. One place where x is negative 0.44, and the other place would be when x is 11.44. Okay, or in other words, the two functions kind of together, like to create a new function by putting them both on the same side of the equation, this function is going to have a 0 at those two locations. Okay, so what I'm going to do now is I'm going to pull up Desmos and we're going to kind of just look at what this looks like on a graph. So again, just to kind of hammer that home, we have x plus 2 over x minus 1. That's our one function. And then we have 2x minus 3 over x plus 4. So one possible way that I can look at this question is to ask, where is the red function equal to the blue function? Where are these graphs equal to each other? So I can see that they cross here at this one place. And look at that. It's at negative 0.44, right? That was one of our answers that we found. And the other place is at 11.44. Awesome, that's the other answer that we got. So we know we feel pretty good about that. And we can see that there aren't any other places where they're going to intersect. You can see that they're both approaching asymptotes on that side. And over here, they're diverging from there. Okay, so those would be our only two answers. So that's one way to view the problem, is to look at where those two functions are equal to each other. The other way is to consider those two functions as one function, where we are subtracting the one term from the other to create a totally new function. And that looks like this. So here's a totally new function. And now the question is not where are two functions equal to each other, because we only have one function, but rather where's that function crossing the x-axis, okay? So that happens, we can see, in two places. One of them is at negative 0.44, which again is one of the answers that we got. And the other time is at 11.44, which is the other answer that we got. So we feel really good about this because we know that our algebra and our graphical interpretations, they all coincide, okay? So two different graphical interpretations for our algebraic approach, so we can see how those things are all related. While we're here, I'm going to point out kind of this conversation that we had a moment ago, is that when we talk about inequalities, we're going to be talking about not just where the function is equal to 0, but we're going to be talking about where the function is above 0. So this would be on this interval, you know, from this value, like the asymptote on the left here up to that point, and also from this asymptote up to that point, and where the function is negative. So on the left of that asymptote, from this point up to the next asymptote, and that's it. Okay, so that's kind of where we're heading next. And so that's why it's easier to look at not just these two functions as independent functions, but rather to look at them as one function. Because if we do that, if we just look at where those two functions are equal to each other, then it's a lot more complicated to talk about where one function is higher than the other or lower than the other. So just setting one side equal to 0 and going from there is just a nice way to kind of tackle these problems in a way that we can always do, that sort of makes that easier to digest. All right, so let's look at another question. So this one is a little bit, more complex, only slightly, but again, we're going to start in the same place. What is this question asking? So two graphical interpretations of that would be one interpretation is, where does this function and this function, where do these functions intersect? Okay, where are they crossing? Actually, truly, it's really only asking for the x value of that point of intersection, because when it just says solve, it just means find the value of x. If the question was find the point of intersection, then we'd have to find the y value as well. But if the question is just solve, then we only really care about the x value. So that's one way to interpret it, is to find where those two functions are equal to each other. So again, long strategy is you could graph both functions and then find where they're equal. And that's totally fine. It's just really long. So we want to have some other strategies as well. Another possible interpretation is to ask not about those two individual functions, but to reframe the question. So to ask a different question, okay? So you're subtracting that term from both sides. When is that new function equal to 0, okay? So this is the new function h of x. Where does it cross the x-axis? So this is a slightly less long strategy, because you can manipulate this left side a little bit so that you really just have one function that you're graphing. Graph the one function, and then it's easy to see where that function has zeros. It's also easy for inequalities to say where is it above the x-axis and where is it below the x-axis. So again, I'm just going to say, like, this second interpretation is really what I want you to be doing. I want you every time to move all the terms over to one side. I don't like that phrase, moving terms over to one side of the equation, because you're not really doing that. What you're doing is subtracting the same term from both sides. But I know students like to use that phrase, so I'll use it here. That doing this is something that, starting this way, by establishing 0 on one side, that will enable you to be able to do the same thing every time, to always start the same way, which always feels good, so you're not memorizing 100 different ways to approach different problems based on how they look. You're always kind of starting in the same place. So that's what we're going to do. We start by having all of our terms on one side of our equation and having 0 on the other side. So now we can view this left side as one function. So before I do that, what I want to do is I want to think back to grade 11 and start the same way as always, is I'm going to start by factoring. Okay. Factoring helps me identify those restrictions. It also helps me see if there's an easier way for me to establish a common denominator, so I'm always going to do that first. So none of these parts can be factored except for the denominator of the first expression, so I'm just going to factor that. So this is x plus 1, x minus 1, because this is a difference of squares, and everything else is really just the same. Okay, so now that I have this factored form, I'm able to state my restrictions. Now I can say x cannot be positive 1 or negative 1. Okay, so I have my restrictions. Cool. Okay, the next thing that I can do is I can establish my common denominator. This is, again, just one of many strategies that you can choose, but I'm emphasizing it because I want you to use this strategy, because you can use it with rational inequalities as well. So we're going to do that. So in order to get a common denominator, we can see it's actually like a little easier to do because I already have a common factor here and here. So I only need to obtain this new part of my denominator in this expression. So I'm just going to multiply this fraction on the top and bottom by that common factor that I'm looking for. So now together they both have the same denominator. So now my numerator is just going to be 2 from my first term there, and then minus x times x minus 1 over here. Okay, and then I know that this whole thing is equal to 0. So now I've established a common denominator. Great. Now I can simplify a little bit. So I'm just going to put that x squared term first. So I have negative x squared plus x and then plus 2 all over x plus 1, x minus 1 equals 0. So that step, I can write that down as simplify. Now that I have this simplified equation, at this stage, if I was solving this as an inequality, from here what I would do is I would need that denominator still, okay? However, in equations, we know, like I said before, the only way to obtain 0 when you're dividing is if the thing you're dividing itself is 0. So that means we only care when the numerator is equal to 0. So I can just kind of like take that and set that apart by itself, okay? So I'm just going to put that here, that the denominator is important when we get to inequalities. And by inequalities, I mean greater than, less than, greater than, equal to, etc. But not really for equations. And that's only because we don't need it to make that value, the value of the function, equal to 0. The denominator is not going to help us do that, because when the denominator is 0, our function is undefined, and that's not the same thing as 0. So a couple different strategies that I could go to use from here, where my goal is solving. Because here I just have a quadratic equation, I could factor, I could use quadratic formula. Here I think it's factorable, so I'm going to start by factoring out a negative. So now that I've factored it, I can say, therefore, x equals 2 and x equals negative 1 are my two solutions. And I feel pretty good about that because they were nice and easy to obtain just by factoring. So now that I have these answers, I definitely need to go back and make sure that I compare these answers that I got to my restrictions. So in that first line, we factored and we saw, oh, we have restrictions at 1 and negative 1. And one of those turned out to be one of my answers. So that means that that answer is what we call extraneous. or we could say, like what we've often said before, is inadmissible. So that means that x equals 2 is our only actual valid answer, okay? This is an extraneous root. It is inadmissible since it's among our restrictions. Okay, so that means this is our only answer to the problem. Now again, let's go back and consider the interpretation of what that means. So, relating this back to the graph, we're asking ourselves, where do these functions equal each other? Where does this equal this? It happens when x is 2. Or we could ask, where does this new function equal 0? That happens when x is 2. So again, let's pull up Desmos. So we have 2 over x squared plus minus 1. And we have x over x plus 1. And so if we're looking at these as two separate functions, then we can see that they intersect at 2. Now, it also looks like they seem to be intersecting at -1. Do you see this? So it seems like they're converging. But if we continue to zoom in, we can see that they're actually never intersecting. That's because both of these functions have an asymptote at -1. And we can see that from the equations. So that makes sense, right? Like this is what this equation is. We can see that these factors don't cancel out, so that there's an asymptote here and an asymptote here at -1 and a +1. Here, we can see that this function by itself, it has an asymptote at -1 and it has a hole at +1. So anyway, because at -1, neither of these functions is defined, they can't cross there. Okay, so even though we found that as an answer, that's not actually a valid answer. And we can see why, because the functions don't actually cross that value. They don't get there. Okay, so if I take this, I'll just call this f of x. And I'll call this one g of x. So if I change the question and I say f of x minus g of x, what does that look like? Well, it looks like this. So let's turn those other functions off. So we can see this is the new function. If I were to, subtract that g of x term from the right-hand side and the left-hand side, so it ends up really only on the left-hand side. So thinking about interpretation 2 over here. Then we have this one graph that we're looking at, and we're asking ourselves, where does that one graph meet the x-axis? Where is it equal to 0? And we can see it happens in one place. It happens at 2. Okay? Again, when we're talking about inequalities, it will be really easy for us to see from here, where is it above 0? Well, on the left of 2 and on the right of that asymptote. And when is it below 0? On the left of that asymptote and on the right of 2. So we are able to see those intervals kind of emerging. Okay, so now let's talk about the big ideas. So the one key thing I want you to get out of this is that there are two interpretations, two graphical interpretations that are kind of worth considering when we're looking at solving rational equations. One interpretation and truly this is equations or inequalities, is to view the left side as one function and the right side as another function, and then to ask where, and when I say where, I mean like for what x value do these functions meet? Okay, so where do they have a point of intersection? Okay, so that's one way to interpret these problems. Another way to interpret these is to ask, and I want to say like a better way, maybe I shouldn't say that. I don't know. Is to change the question to be, if we have like f of x equals g of x, we're going to change this so that we bring all the terms to one side. And then we ask, where does that new function cross the x-axis? Okay, so I really, really, really want you to get in the habit of starting this way, okay? Of always getting in the habit of getting 0 on one side of your equation or your inequality, because there are lots of things that we can do with equations that we can't do with inequalities, and having 0 on the one side all the time is always going to set us up for success that way. Okay, so that's one of our big ideas that we have from this lesson. Now, once you've kind of done this, we know that we can solve these questions graphically. So in method 1, we can graph two functions and we can find their point of intersection. And really, again, when I say point of intersection, I really just mean like the x value where that point of intersection happens. Or if we're looking at interpretation 2, then we can graph the new function that's created by having the two expressions on the same side of our equation, and then find where that new function is on the x-axis. Oops. So again, when I say where, I mean the x value. And yeah, so we can totally do that. And we have all the skills to be able to graph these functions. So absolutely, those are great strategies. We also can solve these algebraically. Okay, so there are a bunch of different methods to do that. So possible methods, like we talked about previously, would be you can cross multiply, you can multiply all the terms on both sides of the equation. By the lowest common denominator. And this is the strategy that the CEMC uses. It's also a strategy that you'll see in your textbook. But the problem with these strategies is that they only work for equations. And we'll talk about why they don't work for inequalities later. But right now, I just want you to know that you're going to be tempted to use these strategies, and it's fine. For equations, you will get the same answer. It's totally cool. But what I really want you to do is I want you to have a strategy that you can use all the time, and that strategy is going to be to establish a common denominator. Okay? So once you've established a common denominator, then you can solve. And ultimately, when you have an equation, you really only need to look at where the numerator is equal to 0. For inequalities, that will be different. But for an equation, you can just say you can solve where the numerator is 0. If solving an equation. So you don't have to really worry about the denominator. So strategies that we have to solve include, if you have any kind of expression that you can factor, then you can solve it by factoring. That might mean that you're actually doing polynomial division, like you're using the factor theorem. If you have a function that's, a higher degree than a quadratic, like a cubic or quartic or whatever. but you won't need those to use with quadratics or linear, obviously, because you'll always be able to do that with those. Like you'll be able to solve them your kind of normal way, or factor them the normal way. But you might want to use them with higher degree functions. Or if it's quadratic, you can use the quadratic formula. Okay, so those are kind of like the main big ideas that I want to get at there, is that, there are two ways to interpret a problem like this, two kind of main ways. We can solve either of those problems graphically by graphing the functions and observing where the solutions are. But it's also really nice to be able to have some algebraic strategies. So we have a couple that are good for equations but not good for inequalities. So this is really the key one that I want you to be emphasizing, which is establishing a common denominator, and then making a conclusion about the numerator having to be 0, because you have 0 on one side of your equation at that point. So the two parts that I've kind of put a box around, those are really kind of where I'm leading you, but I wanted to address that there are other possible methods that you can look at, and you can check out the textbook or check out the CEMC for other more examples that show those other strategies. But again, the ones that I've boxed are the ones that are like going to stick with you as we move forward.